Welcome to the Network Security and Database Vulnerabilities course. Hi, I'm Erica Smith, a course developer for IBM's Identity and Access Management portfolio. I'm here to help you understand what you will learn during each module and lesson to develop your skills in network fundamentals and learn about key terms and database vulnerabilities. Each lesson is taught by an IBM security expert who has the responsibility to train our clients as well as to protect IBM's own systems and resources. These resources are global, and you will learn from subject matter experts in Costa Rica, the United States, and Canada. In this course, you will learn about network basics of TCP/IP and OSI models, DNS, DHCP, as well as switching and routing concepts, IP addressing, NAT, packet sniffing, and finally, structures and vulnerabilities of key databases including SQL, CouchDB, Oracle, and MongoDB. These lessons are designed to cover networking and database basics, so you can confidently enter the cybersecurity workplace. In Module 1, you hear from Moises Monge Marin, a Security Information and Event Management Administrator in our IBM Costa Rica Security Operations Center. Moises will take you through the 5 layers of TCP/IP protocol framework and introduce you to several terms and concepts that will set the groundwork for future lessons in this course. Next, you will learn about network protocols and experience several demonstrations of the concepts to build on the information learned in the first lesson.
In this video, you will learn to describe how a packet is inspected by a stateless firewall.
Today we're going to discuss networking fundamentals and some of the basic concepts of network security. This lecture was developed by Moises Monge and is being presented by Ben Briggs. Let's review some of the differences between stateful and stateless inspection. First, we will focus on how firewalls and routers work in modern enterprises. Then, we're going to talk a little about the differences between an intrusion detection system, or IDS, and an intrusion prevention system, or IPS. Finally, we will cover some of the basics of network address translation routers, or NATs. Regular routers and some firewalls utilize the stateless way of filtering packets. Stateless means that each packet is inspected one at a time with no knowledge of previous packets. No session table is maintained, so each packet is inspected independently of all other packets. So, what is inspected in the packet? The source IP address is examined to see if it's allowed. We may have an ACL rule, an access control list rule, that will determine if that source IP address is allowed into our network, or if the destination address is allowed to be accessed. A check is made to see if the destination port or the service is allowed into the network. Basically, this proceeds packet by packet. Stateless inspection doesn't know anything about session. We will discuss sessions later. There is no database with details of the packets that have already been inspected. Here is an example of a stateless inspection event. We will have our source computer, the client system, bring up its web browser. The web browsers operate in the network application layer. The browser can create TCP or UDP traffic, but TCP is the most common traffic we will see traversing our network. Since our packet is using TCP on network layer 4, it is going to have an IP address. The packet header will contain the source IP address of our client machine and the destination IP address of our receiving computer or web server. Then, the layer 2 information will be added to the packet header. This is information about our local network segment added by the network, such as the physical or MAC address of the source and destination computers and the MAC address of our gateway. Then, the encapsulated packet will be sent to the physical layer, which could be wired or wireless Ethernet. The packet will go to the router, and the router will evaluate the packet. If the source IP address, in this case our client machine, is allowed to access our server, and TCP or UDP are allowed, and if the destination port is allowed, in other words, if our server is listening to that specific service for traffic from outside or even within our company's network, then the packet will be forwarded to the server. What are some of the benefits of a stateless inspection? For starters, stateless inspections are faster than stateful inspections. A stateless inspection gives us a degree of control over what's going on and what is going to be allowed within our network. Stateless inspections are great for troubleshooting purposes when we want to classify packets. Also, they are helpful when we have a router that supports virtualization. We can tell if we have a flow of traffic coming from a specific source trying to go to a specific destination. Then we can send it to a specific virtual instance within our router. Also, we can perform some QRS or quality of service switches, which will prioritize traffic.
In this video, you will learn to describe the additional level of inspection provided by a stateful firewall.
Okay, now let's talk about stateful inspection. Basically, a stateful inspection means that each packet is inspected with knowledge of all the other packets that have been sent or received from the same session. A session consists of all the packets exchanged between parties during an exchange. Sessions have a number of elements, like the source IP address, the destination IP address, the source port, the destination port, and in some cases there's an identifier for the instance, if, for example, your router supports virtualization. So those 5 things define a session. If we see traffic coming in from the same IP address and going to the same destination address, and coming in from the same source port and going to the same destination port, whether TCP or UDP, the firewall will know that these are from the same session and can automatically allow or discard the packet. You can see in this example that a session ID has been assigned. This means that our firewall maintains a database of the session and keeps track of all the packets in the session. And you can see some of the information associated with the session, like the session ID and the policy name. We can configure a timeout value so the session won't remain open forever. You can see the incoming interface, the source IP address, the destination IP address, what VLAN or interface the packet is coming from, how many packets and how many bytes have been used in the session. If there is any network address translation, we will see that information as well. We will also see the outgoing interface. This output is specific to a Juniper firewall. So what happens if we have both a stateless and a stateful inspection? The stateless inspection is going to be performed first, and then the stateful data will be evaluated. What we have here is a diagram that is specific to a Juniper firewall. This is the flow that the packet will follow. If we have an incoming packet that matches the session, the firewall will evaluate the screens. It will see the type of traffic and it will match it against the session. Then NAT or other services that are required will be applied. Some of the services shown are AppTrack, AppDOS, AppQoS, AppFW, and IDP, which are some of the more advanced security services. If the incoming packet doesn't match an existing session, then a different flow will be followed. First, screens will be applied. Screens are basically just filters that will protect against flow or denial of service attacks. Then, static NAT will be applied if that is required. Then the destination NAT if it is configured. Then the routing and the policy evaluation will be conducted. So depending on the incoming and outgoing interfaces that are defined after we know what the route should be, the zones will be defined, and then we'll see if there is a policy that will allow or discard the traffic. In some cases, we might see a reverse static NAT. The source NAT is gone after the policy evaluation. When you're a network administrator, this type of flow is really good to have in mind. Then services will be applied and a session will be built. So you can see when an incoming packet doesn't match an existing session, the path through the firewall is longer. If the packet matches an existing session, its path is shorter because the firewall already knows what this packet is doing.
In this video, you will learn to describe intrusion detection systems, IDS, and how they are used to detect vulnerability exploits on a network. Describe intrusion prevention systems, IPS, and how they are used to actively protect against vulnerability exploits on a network.
This is a symbolic representation of a Juniper brand firewall. Many modern firewalls and network devices have a control plane and a forwarding plane similar to this. The forwarding plane is in charge of forwarding all traffic and making all the routing decisions, the policy evaluations, the session matching, and so forth. This is done in a manner that does not interrupt the control plane, which is in charge of running the operating system, which controls the device and the routing table. If something happens to the control plane, the device will still forward traffic since the forwarding plane will still be running. Let's talk a little about IDS, or Intrusion Detection Systems. An IDS is a network security technology that is designed to detect vulnerabilities and exploits against targeted servers, applications, or a computer within our organization. By default, IDS just listens to traffic. It doesn't take any action. In most cases, an IDS is a dedicated server that's connected to a port on a switch. The switch forwards a copy of all traffic flowing through it to its IDS. The IDS monitors the traffic looking for anomalous behavior, and when found, sends an alert to the administrator. While an IDS won't take any action by default, modern IDSs can be configured to run scripts that can send a command to the router to block an IP address if an anomaly is detected. But normally, an IDS will just send an alert to an administrator to let the administrator know that something anomalous is happening in our network, and then it's up to the administrator to initiate any required action. Now let's move on to intrusion prevention systems, or IPS for short. The primary difference between an IDS and an IPS is that an IPS is designed to take action on its own when an anomaly or an offense is detected in the network. Another difference is that the IPS does not just listen to a copy of the network traffic, but all traffic must pass through it before it's allowed to move on. One disadvantage is that it adds a delay to the flow of network traffic. An IPS is usually positioned right after a router, edge device, or firewall, and some firewalls are designed to also function as an IPS. Unlike intrusion detection systems, an IPS is not a passive listener. It's going to be an active listener, and it can take action if an anomaly is found in our network. IDS and IPS systems commonly use one of four ways to detect threats. IDS and IPS systems both maintain a database of signatures that are used for signature-based detection. These signatures describe common patterns of network traffic that may indicate the traffic contains some malware which warrants raising an alert. Anomaly-based detection is another way to detect a threat in the network. Each network protocol goes about its work in a characteristic way. If we find traffic that does not follow the standards of its protocol, this may indicate a threat is present and an alert is raised. For example, if there are a lot of half-open TCP sessions or HTTP traffic that's not arriving with the right header or arrives with an unexpectedly long header. There are also host-based intrusion detection systems, or HIDS. These are software-based applications designed to protect the computer they're installed on against attack. The HIDS listens to the traffic being received by and sent from the endpoint, which triggers an alert or actions as appropriate. A network-based IDS that listens to a copy of network traffic from a port mirror configured to the core switch, while a network-based IPS sits in the middle of the stream of traffic, both trying to find anomalies in the data stream. The main difference between a host-based and a network-based system is that the host-based system is a piece of software installed on an endpoint machine, while the network-based system is a piece of hardware that listens to all traffic that is sent to it or flows through it.
In this video, you will learn to describe the difference between network intrusion detection and prevention systems and the advantages of each.
Let's review some of the differences between an IDS and an IPS. First is the placement of the device in the network. The IPS is going to be directly in line in the middle of the stream of network traffic. The IPS will be tapping our communication, while the IDS is outside the direct line of communication, meaning it's offline or just receives a copy of all traffic sent to the interface. It is listening in what's called promiscuous mode and analyzing the traffic. Most of the time, this won't cause any delay in network traffic. An IPS, on the other hand, is an active system type, meaning it is usually configured to actively monitor network traffic and to automatically defend the network if a threat is found. For example, automatically creating an ACL or access control list to block traffic that's been identified as malicious. In passive mode, it acts more like an IDS. If a threat is found, it will notify the administrator, and it will then be up to the administrator to take action. An IDS won't normally take any action other than notifying the administrator of a threat. An IDS might have a web interface where the administrator can see what has been found. IDS and IPS systems both use the same detection mechanisms. They both can use signatures to detect malicious traffic, where signatures are basically patterns that can be found in the payload of traffic. Both types of system can also use anomaly-based detection. They will detect if a protocol's standards are not being followed, indicating a threat, or in the case of signature detection, that someone is trying to exploit a vulnerability in the network.
In this video, you will learn to describe how network address translation works, describe the difference between static and dynamic IP addresses and when to use each, and describe the use of IP address overloading and how it works.
Now let's take a look at network address translation, or NAT. This is very common in both home and enterprise level networks. Basically, network address translation masquerades the real IP address, the IP address that's configured on the system, with a different IP address for use on another network. The most common example is when IP addresses from an internal network are translated from the private IP address that is on the computer to an external or public IP address that is routable across the internet. Of course, the reverse operation is performed for traffic coming from the internet that needs to go to a computer on the internal network. This is not always the case. Sometimes we want to translate from a private IP address to another private IP address, or from a public IP address to another public IP address. So, in a nutshell, network address translation does exactly what its name implies. Network address translation is a method of remapping the IP address space by modifying the network address information in the Internet Protocol IP datagram packet headers while they're passing through a NAT router. Basically, the router will read the layer 3 information, and if there is any NAT procedure, it will modify the source or destination IP address. NAT gives us an additional layer of security by preventing the real IP addresses of the systems in our network from being exposed to the world across the internet. Each of an organization's computers could be represented by a different IP address outside the network than is used inside the network, or the entire organization could be represented by a single public IP address, exposing only the IP address of the firewall publicly. NAT is something that is really common in global networking. IP address mapping by a NAT can be performed in a few ways. Here are the most common configurations. Static NAT provides a simple one-to-one mapping between one IP address and another. This is typically one private or internal address mapped to one public or external address. Every time the NAT sees one address, it substitutes the other address that it's mapped to and forwards it on to its destination. Dynamic NAT uses a pool of IP addresses and dynamically maps one of these to the incoming packet. For example, An organization with 100 computers in its network, each with its own private or internal IP address, could share a much smaller pool of public addresses that are used only for packets that get routed outside the firewall to the internet. Finally, we have what's called static NAT overloading. In this configuration, the NAT will map all of the internal IP addresses to a single external or public IP address, so hundreds or even thousands of users will have their local IP addresses converted to a single public IP address when leaving their local network. This can work because the NAT also assigns a unique Layer 4 source or destination port number to each IP address it maps, so it can properly differentiate between all of the local users who are now sharing the single public IP address. This process is also known as port address translation, or PAT. Obviously, this means that the NAT must maintain a database to keep track of all the addresses and port mapping that it has assigned, so returning packets can be properly translated back to local IP and port information, so they can be properly routed once back inside the local network.
In this video, you will learn to describe how Ethernet networks work, describe the difference between the Layer 2 and Layer 3 addressing schemes.
Greetings! Today we're going to discuss Ethernet and local area networks. This lecture was developed by Moises Mong and is being presented by Ben Briggs. Let's talk about Ethernet and LAN. This lesson will be an introduction to the local area network. Our objectives will be to describe how the Ethernet networks work, understand the various network devices and differentiate between them, understand the difference between a collision and a broadcast domain, describe different ways of segmenting broadcast domains, understand how virtual local area networks work, understand the different addressing schemas used in modern networks. The two different addressing schemas just mentioned are shown here. One on Layer 2, the data link layer of the OSI model, and the other on Layer 3, the network layer. The data link layer uses MAC addresses, while the network layer uses IP addresses, which could be IPv4 or IPv6 format. The way a packet is delivered from one network to another, from one host to another, can be compared to the way the postal service delivers mail. We will put a message inside of an envelope, which is similar to the way the data is encapsulated within one packet header, and then the header is encapsulated within another header. The IP packet is then encapsulated on an Ethernet frame at the data link layer, or another type of Layer 2 frame if something other than Ethernet is being used by the network. And finally, this is all encapsulated one more time with physical information added at the Layer 1, the physical layer. This is similar to the way we put the message we want to send inside of an envelope and write our address and the destination address on the envelope, including the city, state, country, and postal codes. The post office puts your envelope in a shipping crate destined for the postal code and marks that code clearly on the outside of the crate. The post office will search for the shortest and most efficient route to get the crate from its current location to the post office designated by the destination postal code. This is similar to how a Layer 2 device, a router, searches for the most efficient route for sending your message across the network or the internet. Once the shipping crate has been received by the destination post office in the country, state, and city you specified, your envelope will be removed and driven to the street and the house or apartment number specified and placed in a mailbox. Your friend will receive the envelope, open it, and read your message. As you can see, each step taken to encapsulate your message prior to it actually being sent is undone one step at a time in reverse order at the receiving end. The Layer 2 address and Layer 3 address are quite different. Layer 2 addresses are known as Media Access Control or MAC addresses. MAC are also referred to as hardware addresses, physical addresses, or burned-in addresses because they are permanently etched into every network interface card and are unique to that card. Of the billions of network interface cards ever produced, no two have the same MAC address. This is an example of a MAC address, which is a 6-octet address for a total of 48 bits. Every time a packet passes through a Layer 3 device, like a router, and passes from one network to another, the Layer 2 information in the packet header is stripped out and replaced with new physical source and destination addresses. The Layer 3 address is the IP address, which is also known as the illogical address. This is an example of a private IPv4 address that is not routable on the Internet. Layer 3 addresses identify computers or endpoints and do not change as the packets are routed, with the exception of substitutions made by NAT routers, of course. Let's look at how local area networks work so we can better understand the connections between devices and the rules controlling their communication. In order to deliver information from one host to another within the same local area network, we need to know the MAC address associated with the IP address of the destination device. Let's jump on our server and take a look. Let's say we want to ping this address, 192.168.52.2. Ping, or Packet Internet Groper, is a utility that measures the time it takes to send a packet to another computer and receive a response back. And it's the easiest way to quickly test if there's an open communication route between your computer and another system. You can see that the ping was successfully delivered and we've received a response. You can ping an IP address because the Address Resolution Protocol, or ARP, is able to make an association between the IP address we typed in and the MAC address that you can now see on the screen. This works fine for communication in our local area network, but when we need to deliver a packet outside our local area network, the default gateway is the device that will make sure the packet is forwarded outside of the local network. Now let's try to ping 4.2.2.2, an address which is outside of our LAN. But the default gateway address is not found in our ARP table, which is why the ping did not succeed. No default gateway means no packets get routed outside our local area network. To summarize, in order to deliver a message to any computer within our LAN, whether the packet originated from a computer within the LAN or was routed to our LAN from an outside network, we need to know the MAC address that was associated with the destination IP address.
In this video, you will learn to understand the difference between collision and broadcast domains. Describe the different ways available to segment broadcast domains.
In order to connect to a local area network, we need to connect through a medium on layer 1, the physical layer. This could be wired using an Ethernet cable, for example, or it could be a wireless connection. The frame, or header of layer 2, the data link layer, contains the source and destination MAC IP addresses, the protocol type, whether we're using IPv4 or IPv6, etc., the data itself, and the checksum. The checksum is a number that's calculated by an algorithm that looks at the data being transmitted after the frame is encapsulated. The receiving host recalculates the checksum on the received packet as a way of making sure that the packet is not changed in any way during transmission. If the packet is changed, it is dropped, or a request is sent to transmit it again, depending upon the upper layer protocol being used. All modern networks support full duplex communications, so computers can send and receive data at the same time. Some older networks did not support full duplex and only supported half duplex, which limits the computer to switching back and forth between sending data and receiving data. To deal with half duplexing, the old networks used a protocol called Carrier Sense Multiple Access Collision Detection. This protocol would detect if it was okay to transmit data, and it would detect when collisions occurred. If there was a collision, it would simply wait for a random period of time and try again. The protocol is not needed in today's networks, since everything is full duplex and we can send and receive packets simultaneously without collisions. So, how does a NIC know if a packet is intended for its computer? The receiving computer takes the data and moves it back up the stack one layer at a time. Layer 1 converts the electronic signals to digital bits and forwards the frame to Layer 2, the data link layer. Layer 2 checks to make sure the destination MAC address matches its own MAC address And if it does, it strips off the layer 2 header and forwards the data as a packet to layer 3, the network layer. Layer 3 checks to make sure the destination IP address matches its IP address, and if it does, it strips off the layer 3 header and sends the packet on up to layer 4. If either the destination MAC address or the destination IP address do not match the receiving computer's MAC and IP address, the packet will be discarded as not being intended for this system. Let's touch briefly on the Internet frame preamble. The preamble is the first 8 bytes of an Ethernet frame. The first 7 bytes are just a series of alternating ones and zeros. This is used as a buffer to separate adjacent Ethernet frames, and it helps the network regulate the speed at which the data is sent. The last byte of the preamble is called the Start Frame Delimiter, or SFD. The SFD lets the receiving computer know that the preamble is over and what follows is the actual frame contents. This is an example of a MAC address. Remember, this is a 48-bit address divided into 6 octets. The first 3 octets make up the organizationally unique identifier. This uniquely identifies the manufacturer of the NIC. The remaining 3 octets are assigned by the manufacturer as the unique identifier for this specific card. Combine these 2 sets, and every network card ever made has a unique MAC address to identify it. When a computer receives a frame, the first thing it does is look at the destination address. If the destination address matches its own MAC address, it will pass it up to the next higher layer protocol. If it does not match, it will drop the frame. There are several types of communication that can go on in a network. Unicast is a one-to-one communication between only 2 computers. Broadcast is when one computer sends information to all the computers on the network using the broadcast IP address. And then there's multicast. This is a one-to-many configuration where endpoints are subscribed to a service to receive the messages sent by the one computer. This is useful when you want to send different messages to different groups of computers that are all on the same network.
In this video, you will learn to differentiate and understand the variety of network devices we have, understand how the virtual LANs or VLANs work on a local area network.
Let's start by looking at something very basic, the cabling that connects your network devices together. 2 of the more common cables you will see in networking are the coaxial cable and the twisted pair cable. Coaxial cables normally use an F-type connector, while twisted pair cables usually use an RJ45 connector. Twisted pair cabling, shown here with an RJ45 connector, are the most common cables used in local area networks, where the length of the cable doesn't need to exceed 100 meters. Twisted pair Ethernet cables are rated for both speed and length using a CAT rating system. Cat5, for example, is rated for transmission speeds of 100 megabit per second for up to 100 meters. Cat6 and Cat6a, on the other hand, are rated for network speeds of 1 and 10 gigabit per second, respectively, over the same distance. There are several common types of network device. A repeater, also called a hub, is a dumb device. When a repeater receives a frame, it will forward that frame across all of its interfaces. So the frame will be received by all of the endpoints that are connected to that device. And it's up to each endpoint to check to see if the frame sent to it is intended for it or not by evaluating the layer 2 MAC addresses on the frame, as we saw in the previous video. A hub will regenerate the signal before sending it on, so the signal leaving the hub will be clean and full strength. Since a repeater has no intelligence, it cannot check to see if it is safe to send a signal at any point in time, so collisions are inevitable. When collisions are detected, the receiver will have to signal the sender to resend the packet, which of course slows down communication across the network. It's very unlikely that you will see a dumb device like a repeater or a hub on a modern network. A more advanced type of network device is a bridge. A bridge is similar to a hub, but a bridge does not send the signal to all connected ports, but only to the port the destination computer is attached to. By maintaining a MAC table, the bridge knows which machine is attached to each port. A MAC table is not the same thing as an ARP table. The bridge looks at the layer 2 destination MAC address of the incoming frame and matches that to the connected port as assigned in the MAC table. So a bridge is a device that can be said to add some intelligence to a local area network. To review, a bridge maintains a database called a MAC table and uses the MAC table to match the MAC address on the incoming frame to the port on the bridge where the matching destination computer is connected. All of the devices attached to a hub are in a single collision domain. A bridge adds intelligence to the network by breaking up the collision domains. Each port on the bridge creates an independent collision domain. The more modern version of a bridge is called a switch. While a bridge has some limitations, for example, a bridge is a half-duplex device, meaning that the data can only be sent in one direction at a time, so computers attached to a bridge can either receive or transmit at one time, but not both. Another limitation to a bridge is that the endpoint devices connected to the ports on a bridge must share the available bandwidth. And finally, virtual LANs or VLANs are not possible. Switches are the most common network device in modern networks. Switches use full duplex communication so they can transmit and receive data at the same time on each port. Each port is dedicated to a single device, so bandwidth is no longer shared. And VLANs are now possible on a switch, which means that we can implement a logical segregation of broadcast domains in the same device. VLANs now provide a way to separate LANs on the same switch. Devices in one VLAN do not receive broadcast messages from devices that are on another VLAN. VLANs are basically a way to logically break down broadcast domains. Switches do have some limitations too, of course. When there are multiple switches connected together as part of the same network, network loops are still a problem. In such cases, protocols such as the spanning tree protocol can help out. Switches might not improve performance with multicast and broadcast traffic, and switches cannot connect geographically dispersed networks. So this is a wrap-up of local area networks. Thank you very much. Today we're going to discuss the basics of network routing. This lesson is being presented by Ben Briggs and is based upon a lecture series developed by Moises Mong. Now we're going to talk a little bit more about the very basics of routing, how a packet is passed from one computer to another within your local network or to anywhere in the world. The learning objectives for this lesson are: understand Layer 2 and Layer 3 addressing, understand the interconnection of broadcast domains using the Layer 3 devices, that is, routers and firewalls, describe the address resolution or ARP protocol, understand packet forwarding through different broadcast domains.
In this video, you will learn to describe how TCP/IP Layer 2 and layer addressing works. Describe the difference between an IP address and a MAC address. Describe broadcasting domains and how they are used in network routing.
If you look inside your computer, you'll see a network interface of some sort. It may be a single chip or a whole network interface card. Your NIC could support a wired connection, a wireless connection, or both. The NIC will always have a burned-in address, which is also known as the MAC address or a physical address. The MAC address is physically encoded on the card and cannot be changed. A student recently pointed to MAC spoofing and asked why I would say that a MAC address was burned in and could not be changed. Well, it's true that the MAC address is burned into a NIC and cannot be changed. Many operating systems can be tricked or configured into representing the MAC address of their interfaces using a different address. This is known as MAC spoofing and can be used to bypass MAC address filtering that's set up on a firewall to protect assets by limiting access to only those machines that have been previously granted access. To be successful, the bad guy has to know the MAC address of a system that has access through the firewall first, and then configure his system to communicate using the stolen MAC address. The MAC is 48 bits long, or a string of 48 ones and zeros. This address is divided into 6 octets, or 6 groups of 8 bits each. The first 3 octets are reserved to identify the manufacturer of the NIC and are called the Organizationally Unique Identifier, or OUI. The last 3 octets are used by the manufacturer to identify each unique card. With more than 300 million new devices connecting to the Internet each month, we might wonder if we risk running out of available MAC addresses. Well, 2 to the 48th power is about 281 trillion, so at the current rate of consumption, we have just under 1 million months to go before we run into trouble with MAC addresses. To see your computer's MAC address, open a terminal or command prompt window. On Linux systems, run the ifconfig command. On Windows systems, run ipconfig/all, and the physical address is clearly listed among the many other parameters and addresses. In this example, we'll use Secure Shell or SSH to connect to the router. I enter the password, and we see the information for all the interfaces. Remember, each individual network interface has its own address regardless of how many network interfaces are in a single device. So looking more closely at this one, we can see the Layer 2 MAC address. This is the physical address or MAC address of my system, and this is the broadcast address that can be used to send a message to all the devices in this network segment. Notice that the MAC address does not appear as 6 groups with 8 ones and zeros in each group, but has been condensed by representing each binary octet by 2 hexadecimal or base 16 numbers instead, to make them easier for us humans to work with. The computer still sees the 8 ones and zeros, but displays only 2 hex numbers for our benefit. When a packet is sent from one computer to another, the packet header will contain both the Layer 2 and the Layer 3 address. The packet is actually delivered to the Layer 2 or MAC address, and the computer then verifies that the Layer 3 or IP address in the header matches its own assigned IP address. The system then checks to make sure the Layer 2 MAC address in the packet header matches that of the system, and if it does, it will start processing the packet. When we talk about broadcast domains, we are talking about the segment of the network that our computer is on. Looking at the router we logged into, we can see that it has many network interfaces. We have the ENP0S3, ENP0S8, and ENP0S9. So this device is connected to 3 different networks, which means 3 different broadcast domains. You will see what my local IP address is, what the broadcast address is. If the packet is sent to the broadcast address, all the endpoints within that broadcast address will receive the packet. Broadcast domains can also be called virtual LANs or VLANs.
In this video, you will learn to describe the address resolution protocol and how ARP tables are used in network routing.
Let's go a little deeper into ARP, the Address Resolution Protocol. This protocol is really quite simple. ARP takes an IP address as input and returns the MAC address of the computer that the IP address is assigned to. We're going to take a look at the ARP table on the Linux router. But you can see the ARP table on your own Windows, Linux, or Mac OS X system by running the ARP-A command in a terminal or command prompt window. This Linux router has its own set of commands to show this information, so I'm going to run an IP neighbor show command. This displays all of the MAC address information there is on this device. For this IP address, 172.16.52.1 is connected to ENP0S8, and it has a logical or MAC address as shown here. And we can see that ENP0S8 is within the broadcast domain or local network. So this is ENP0S8, and you can see that 172.16.52.101 is the CIDR range. Let's say that we want to ping a device within that network, but we don't have translation of the IP address or MAC address working. Let's see what actually happens. So I'm going to start a TCP dump on the interface ENP0S9 on another screen to capture traffic information. We're going to pipe this to a PCAP or packet capture file and then leave it running. Before we do anything, let's quickly recheck our ARP table. Now let's ping a device that's not listed in our ARP table. 192.168.52.100, and then let's see what happens. We can see that that ping is successful. Now it's time to stop the capture and see what we caught. Transferring that PCAP to my desktop. Okay, great, here it is. So the first thing that we're going to see is that before a ping can be successful, the computer needs to get the physical address of the target IP address, because a packet is never delivered to an IP address, but always to the physical or MAC address. So the first thing a computer does when trying to ping an IP address, 192.168.52.100, is to try to find its MAC address. So your computer queries all other computers on its local network. You can see the source address is here and the destination is broadcast. So this frame will be sent to all other devices in its broadcast domain. Whoever has the address 198.162.52.100 is supposed to let us know if that device exists on our network, i.e. who has this IP address, and this is my computer, 192.168.52.4, that's initiating the ping, the address you need to respond back to. If I go again to the router I was logged into and inquire, you will see that this is my IP address. So this is me asking, who has this IP address I'm trying to ping? And fortunately, for the sake of this demo, we do receive an answer. The answer here on line 2 comes from the computer with this MAC address. And the message is sent to my MAC address, which you can see here. So the message says 192.168.50.100 has this MAC address. Once we have our own ARP table populated with that translation, then the ping can be transmitted. Here you can see the Internet Control Message Protocol, or ICMP, echo request, and an ICMP reply. So this is how the Address Resolution Protocol works to translate IP addresses into the MAC addresses needed for systems to communicate. Here's an example of an ARP table from a Windows machine. On a Windows machine, you issue the command ARP-A in a command prompt window, and you will see the ARP table. We can also see this data on a Wireshark packet sniffer. You'll see the same thing we saw earlier when showing the live packet capture. This is an example of a response which we can see here. If I select this packet, you can see the Address Resolution Protocol and the reply. As you can see, this is IPv4, and this is the source MAC address for this packet. This is the source IP address, and this is the destination. In this case, it's our router. And you can see that it has for a destination our IP address and also our MAC address. Something important to keep in mind, the MAC address of the destination is only required to transmit data within the same broadcast domain. When we're sending packets to a different broadcast domain, the only MAC address that we need is the MAC address of our default gateway, which in this case is our router. For this reason, let's look at the routing table. In this case, our default gateway address is 10.0.4.2. If we want to ping google.com, we do not need to find the MAC address of google.com, but we do need to get the MAC address of our default gateway, which is 10.0.4.2. Just to double check, yes, we have it. So to sum up, the ARP protocol works to find machines within the same broadcast domain.
In this video, you will learn to describe the use of routing tables in network routing.
Our next goal in mastering network basics is to gain a better understanding of routing and the use of routing tables. When we think of routing tables, it's natural to assume that they're just for routers. In reality, though, each and every computer connected to any network, whether it's an endpoint or a server, will have its own routing table. So let's take a closer look. This is a virtual machine that is working as a router for this demonstration. You can view your routing table by issuing the netstat-nr command. This works on Mac OS X or Windows systems from a terminal window. The router is running CentOS, so I'll enter an IP route show command. This is all we have in the table at this time. If we want to send a packet to an IP address that is not listed here, then we will send it to our default gateway, and the default gateway will make sure the packet is delivered to the next hop. But if we want to send a packet within this network, the ENP0S9 interface will take care of anything that exists within this broadcast domain. We also have interface ENP0S8 and ENP0S3 with their respective broadcast domains connected to this router. One of these is just another endpoint, but the other is our default gateway. In this example, this device is just a switch connecting all these computers. Recall that switches use MAC tables. So when a switch has to deliver a packet to a computer, it does not even look at the layer 3 information, but just looks up the layer 2 MAC address in the packet header to see if there is a corresponding entry in its own MAC table. If the MAC address exists, the packet is delivered to the corresponding interface.
In this video, you will learn to describe how routing tables and default gateways are used to forward packets between broadcast domains.
Okay, so a little more on routing tables. Here we have a broadcast domain called Network 1, which is connected to a layer 3 device, in this case a router, but it could be a firewall or a switch. This router is also connected to Network 2, which is also broadcast domain 2. And Network 2 is connected by a second router to Network 3, which of course is a third broadcast domain. So if a computer in Network 1 wants to send a packet to a device in Network 3, it only needs to have a default route configured pointing to its default gateway, which is port 1 of the first router. This router will check if the device 1.8 wants to send a packet to device 3.6 in Network 3, for example, and the first router is not directly attached to device 3.6, it will send the packet to its own default gateway, which in this case is port 1 of the second router. The second router will know that device 3.6 is directly connected to its port 2 and will deliver the packet. This router must have its ARP table populated with device 3.6's MAC address. To keep it simple, let's call that MAC address AD. For device 3.6 to be able to respond, the second router will have to know the path back to the device 1.8 via the first router. So if device 1.8 pings device 3.6, the path forward and the path back will both have to exist in order for device 1.8 to receive a reply.
In this video, you will learn to describe the different types of routes defined in a routing table. Describe how MAC addresses show up in a system's ARP table. Describe in detail how a network knows exactly where to forward packets successfully.
Welcome back. Now let's talk a little more about routers and routing tables. There are different types of routes defined in a routing table. In the last video, we saw 3 different route types on a single terminal and router. So let's check again on these routes. There are 3 routes. The default route is used to send packets to addresses we have no other information about. For example, if we send a packet to IP address 4.2.2.2, we don't know anything about this network, so the packet will be sent to the default gateway. The default gateway for this subnet is 10.0.4.2. Send the packet there, and the default gateway will take care of routing it to another network. The default gateway is doing a good job, as we can see, since we're getting a successful reply to our ping. We also have 3 more routes shown, which are directly connected to our server. So this is saying that this network exists connected to this interface, and the same for these other 2. So these are 2 different types of routes. Routes to systems that are directly connected to our local network, and routes through our default gateway. Of course, there are more than 2 types of routes. There are dynamic routing protocols like OSPF, RIP version 1 and RIP version 2, EIR GRP, which is a Cisco proprietary protocol. Looking again at our example of someone trying to send data from network 1 to network 3. This is a small network that's about as simple as a network can be, containing only a router and server 100 and server 200. We use SSH to log in as root to server 100 at IP address 192.168.52.100. From server 100, we want to ping server 200. Service not known means we don't have the DNS translation enabled, but we know the IP address of server 200. It's 172.16.52.100, so we can ping that. You can see the ping is successful. Now let's check the routing table to see how the router is making sure that this packet is delivered to server 200. We can see now what the router is doing. There isn't a route that points directly to 172.16.0.0. That's where we're trying to ping. But we have our default gateway connected to the interface ENP0S3. So all that's happening is the packet's being sent to our default gateway, and the default gateway is making sure this packet is delivered. The default gateway is also going to make sure the reply is routed back to us. We can run a trace to see exactly how this packet is routed from the local host through the gateway, and the gateway is making sure that the packet is delivered to its destination endpoint. You can see here that 172.16.52.0 is not directly connected to our interface. In this case, we only have one interface. We have the loopback, which is a logical interface, and we have ENP0S3, which is the physical interface for this device. There are two IP addresses assigned to the same interface, which is perfectly valid. And here is our MAC address. If we check the ARP table, we'll see that the ARP table is only populated with devices that are directly connected to our interfaces, meaning from the same broadcast domain. In this case, the only interface we have within this network segment of 192.168.52.3/24. So our ARP table is populated with only that address. Even though we're pinging 172.16.52.100 and the ping is successful, the 172 address will not be added to this ARP table. Again, the ARP table will only translate addresses within our local broadcast domain. What we need to know when sending data to a remote IP address is the MAC address of our default gateway. In this case, when we check the routing table, our default gateway's IP address is 192.168.52.4, and we can look up that address translation in the ARP table. The entry for this IP address is the physical address 0800278464A5. As should be obvious by this point, each IP address will have a different MAC address, because the MAC address is the physical or burned-in address for that interface. So that's how we can send packets across the different network segments. Our default gateway will make sure that the packets are delivered to the closest layer 3 device until it finds a layer 3 device that has the destination system directly connected to one of its interfaces.